All right, so welcome back to the session. So in the second half, we have 6 presentations. The first one was taken by Qiang. So they will talk about experimental investigation of a patient thermofluidic oscillator with pumping pump for low-grade heat recovery. If you are ready, so yeah. So I will set a 15-minute timer. So I will stand up for about 50 minutes and you have 2 minutes to render.
Okay. Thank you, Chair. Good afternoon, everyone. I'm Qiang Zhou, a PhD student at Zhou University. So I'd like to introduce my recent work on heat engine. Furtherly, motivation. Thermofluidic engine is a type of heat engine that can convert heat to acoustic work. It is a heat engine that periodic thermodynamic oscillations such as pressure and volume flow rate are induced by external temperature difference. The structure of thermofluidic engine is quite simple. Consists of a cooler, regenerator, heater, and several tubes. Thanks to the notable merits of stability, environmental benign, and simple structure, the thermofluidic engine has attracted much attention from both researchers and industries. To illustrate how heat converted to sound work, here I present a simple experiment. So this part is a wet tissue that pre-soaked in water to be a cooler, and the steel wool represents the regenerator, and we heat one side of the steel wool. This is the sound that the heat converted. If we lower the temperature, the sound disappears, and when we reheat again. Yeah, this is quite interesting thing. So we can use a simple structure to convert heat to mechanical work, and actually in the early 19th century, Lord Rayleigh gave the first explanation of thermoacoustic oscillation, stating that if the phase angle of liquid's motion and heat transfer are appropriate, the vibration may be maintained. And since then, a lot of researchers are studying standing wave thermoacoustic engines and traveling wave thermoacoustic engines. In standing wave thermoacoustic engine, the phase difference between pressure and the water flow rate is 90 degrees, while in traveling wave thermoacoustic engine, the phase difference between the pressure and water flow rate is only 10 degrees. So the traveling wave thermoacoustic engine can realize a reversible thermodynamic cycle that is similar to a Stirling cycle. In 1999, Backhouse and Swift invented the thermoacoustic Stirling engine. It can achieve a maximum thermoacoustic efficiency of 30%. One of the biggest challenges for thermoacoustic engine is that its operation temperature is relatively high for the traditional heat engine. So a lot of researchers are dedicated to lowering the onset temperature difference, which means the lowest operating temperature difference. One of the efficient ways is introducing liquid vapor phase change process. The researchers pre-soak the regenerator in water, but the engine is hard to stabilize since the water is vaporized. So it leads to a big challenge for practical application of phase change thermoacoustic engine. To address this challenge, we firstly designed a 2-phase thermoacoustic engine that can operate at low temperature difference, and also it can operate for a long time. And then we investigate the influence of the low tube and mean pressure on onset and steady state performance. And finally, the pumping performance of the engine is also characterized. Now let's move on to the experimental system. The thermoacoustic engine we built is quite simple. It consists of a acoustic engine and a pumping line. We can see that the thermoacoustic engine consists of a loop tube and a phase adjustment unit. The phase adjustment unit is to make sure the phase in the regenerator is close to a traveling wave phase. And we hit one side of the regenerator and we cool the other side of the regenerator. And when the temperature difference in the regenerator exceeds a critical value, just like we showed in the video, vibration is induced. So the gas in the vapor tube just oscillates, and then we can use this oscillation to pump water. The pumping line consists of two check valves and several tubes. The right figure shows the photograph of the pumping line and the thermoacoustic engine. In the early 19th centuries, in the early 20th centuries, Resbeck and Selecton proposed the West thermoacoustic theory. Based on the West thermoacoustic theory, we further introduced the first order pressure oscillation in the thermoacoustic engine, and then we rearranged the equation to linearize the momentum and the continuity equation. And then, since we know that the oscillation, the resonance frequency of the engine is below 1 Hz, so we can model the engine by the long parameter model. The right figure shows the acoustic electric analogy circuit. This part is the regenerator, and the other part also represented by the capacitance, resistance, inductance. By adopting Kirchhoff's law to this circuit, we can calculate the offset temperature difference and also the resonance frequency. Finally, the results and discussion. First, we investigate the effect of load tube length on the offset temperature difference and the resonance frequency, and also the pressure amplitude. Since the load tube length not only improves the acoustic field in the regenerator, in the thermoacoustic engine, but also it affects the viscous loss in the engine. So we investigate the effect of load tube. Firstly, we can see that both experimental and the theoretical temperature difference, it decreases first and then increases with the increasing load tube length, but the resonant frequency decreases with the load tube length. This is because an increased load tube length leads to a higher acoustic inductance. And we can find that at a tube length of 1.5 meters, we can obtain a maximum pressure amplitude of 9.4 pascal. And then we investigate the mean pressure effect of mean pressure on the onset and steady state performance. We can find that the maximum pressure amplitude we obtain is 7.1 kilopascal at a temperature difference of 90 degrees, and the maximum liquid displacement is 211 millimeters, which is also triple of our previous works. And the pressure amplitude is almost 6 times than our previous work. And finally, the pumping performance. We use the thermoacoustic engine to pump water, and the maximum pump flow rate is 80 kilograms per hour at a temperature difference of 90 degrees or 80 degrees, and the highest thermal efficiency we obtained is around 0.6%, and the highest relative caloric efficiency is around 3%. So finally, this is just an initial experimental investigation of the proposed engine, but we can find there are some notable advantages of the engine. Firstly, it can operate at a low temperature difference, which is below 100 degrees. So in the future, we can add a sunlight driver heater to heat one side of the regenerator, and also it has no solid moving parts, so it has low operating costs and easy to to maintain it. And also the working fluid of its air and water, so it shows a good effect to the environment. And finally, the conclusion part. Firstly, we designed a two-phase thermoacoustic engine that can operate at a temperature difference of around 50 degrees, which is beneficial for recovering low-grade heat. And then the maximum water pump flow rate is 80 kilograms per hour at a temperature difference of 80 degrees. And the highest relative canal efficiency is around 3%. We should know that since the part of heat is used for the phase change, so the efficiency is satisfied. So the two-phase thermoacoustic engine shows promising potential for water pumping applications. Thank you. That's all.
Thank you for the presentation. Questions? So your results, I think there are some differences between experimental and modeling results. So you have any thoughts, like, if you want to improve the modeling accuracy, and how that may help you further.
Yeah. So a really good question. Thank you. Just as you mentioned, in the modeling, firstly, I just ignored the effect of heat exchanger and the hot heat exchanger and the cooler. So in the future, I will add them both in the model. Yeah.
Also for the efficiency, I'm not an expert. Can I share, like, regarding efficiency, how it compared to some other alternative, low temperature, like heat engine, like regarding common efficiency? Yeah.
Actually, the common efficiency is relatively low, since the temperature difference is far away from the organic function cycle. But anyway, I think the advantage we focus on is like no soluble mass and maintenance. So we must sacrifice something.
Okay.
Yeah.
Yeah.
But I think there is still a lot room for us to improve the engine.
Okay.
It's more like a novel heat technology.
So with no question, let's start the speaker.